In a way, this section of the book is kind of like the last section of the book, where at the very beginning of the book, we started with the notion of average rates of change, and we use that to define the derivative, or to give us the intuition for how to define the derivative. But in the last section, things kind of went backwards because we have such nice formulas for calculating derivatives. Even though we define the derivative using the notion of average rate of change, we found that the ease with which we can calculate derivatives lets us go backwards and take the derivative and use it to approximate average rates of change. This is another section that's kind of backwards like that. We, of course, use the notion of limit to define the derivative. But in the end, we end up with all these nice derivative formulas, and kind of bizarrely, those nice derivative formulas now let us calculate limits more easily than we could have before, certain kinds that are distinctly non-obvious. The rules that we're going to talk about, it's one theorem. It's called lHopitals rule. As a fun little historical remark, lHopitals rule. You see it written with an S and without this accent, without this caret over the O in some sources. L'Hôpital actually spelled it with the S and without this accent mark, but French has changed. In modern French, there's no S and there's the accent mark, so which way should you write it? Well, just understand, both are kind of right. All right, L'Hôpital's rule. Now, what's it for? It's for these limits when, I'm going to say the very unclear, the very imprecise limits when plugging in yields an indeterminate form, which we talked about way back when we did limits, but I'll remind you, yields an indeterminate form. So the big ones that L'Hôpital's rule deals with is when you end up with 0 over 0, or plus or minus infinity over plus or minus infinity. What do I mean when you plug in and yield this? So I mean things like the limit as t approaches 0 of sine t over t. Right? If you just plug in t equals 0, you get sine of 0 is 0 and t at 0 is 0. So if you just plug in, you get 0 over 0. Or something like the limit as x approaches infinity of x over e to the x. As x goes to infinity, well, this numerator goes to infinity, e to the infinity goes to infinity. So this is one where you think, I get the indeterminate form, positive infinity over positive infinity. Does that mean that these limits are undefined? Absolutely not. Yes, 0 over 0 is undefined, this is undefined, but the fact that when you plug in that you get one of these, the limit could be almost anything. There are cases where you plug in and you get this and the limit's infinite, or it's 0, or it's anywhere in between. How do you evaluate these? You use the tricky thing, or the nice thing, you use L'Hôpital's rule. So suppose we've got f and g, and they're differentiable. Suppose f and g are differentiable. So their derivatives exist. We only need this near where we're taking the limit. But I'll just briefly say, suppose they're differentiable. And either, well, there's one case where f of c equals g of c, so c is some number that we're going to approach, equals 0, or the limit as x approaches c of f of x is plus or minus infinity, and the limit as x approaches c of g of x is plus or minus infinity. then, well, actually, let me be very careful and say, suppose the limit as x approaches c of f prime of x over g prime of x is L, where L could be a real number or plus or minus infinity itself. Then the limit as x approaches c of the original functions, f of x over g of x, also equals L. So it equals the limit of the quotient of the derivatives. Do not confuse this with taking the derivative of the quotient. So the conclusion of lHopitals' rule is that this limit is the same as the limit of the quotient of the derivatives. So the limit as x approaches c of f prime of x over g prime of x, under the assumption that when you plug in c here and c here, you get either 0 over 0, or that as you take the limit of this as x approaches c, you get plus or minus infinity, and you get plus or minus infinity here. The conclusion is that this limit equals this limit, provided this limit exists. This is the limit of the quotient of the derivatives. That is not the derivative of the quotient. There's no quotient rule going on here, which might look a little weird. And because this does look so weird, I'm going to prove what is absolutely the easiest case. The technical proof of the general case is much harder. But the easy case is pretty easy. Before I go on, because I don't want to forget to say it, in lHopitals' rule, the rule still holds if you take limits just from the right as you approach c, or limits just from the left. You don't need to take the two-sided limit, and that comes up in applications fairly often, that we could put from the left here and here, or from the right here and here. Okay, so what do you get? Or how do you prove this? Proof in the easy case. What's the easy case? The easy case is, suppose, the really easy case, we'll suppose f of c equals g of c equals 0, and the limit as x approaches c of f prime of x over g prime of x equals f prime of c over g prime of c. And this is what I called L in the statement of the theorem. Okay, so we're going to assume that this is true, that we're in the case where if you plug in c, you get 0 over 0. And there's also an extra assumption here that the limit as x approaches c of this quotient is actually what you get when you plug in c into the numerator and denominator, which means we're assuming the derivative here is continuous, the derivative there is continuous, and that g prime of c is not 0. Okay, how do you prove lHopitals' rule in this case? This case actually does give you a good feel for why lHopitals' rule should be true. Makes it a little less mysterious. But really, lHopitals' rule, what we care about are applications for calculating limits that would be very problematic to calculate without it. So we want L. It's f prime of c over g prime of c. By definition of those derivatives, this would be the limit. Well, this is the limit as x approaches c of f of x minus f of c over x minus c. This is one way of writing the formula for the derivative. And this derivative of the denominator is the limit as x approaches c of g of x minus g of c over x minus c. Now, we're assuming that these individual limits exist, but then we have that the limit of the quotient is the quotient of the limits. That if these individual limits exist and the bottom one's not 0, which it's not because we were saying that that quotient is L, then this is the same as the limit as x approaches c of just one big limit of the quotient. So this. But then you can cancel the x minus c's. This is the same as the limit as x approaches c of just f of x minus f of c over g of x minus g of c. But we're assuming that f of c and g of c are 0. We're assuming this and this are 0. So this is the limit as x approaches c of f of x over g of x, which is what we were trying to show. That, yeah, the limit as x approaches c of f of x of g of x is the same as f prime of c over g prime of c, or what's the same thing, the limit as x approaches c of f prime of x over g prime of x, because we made this assumption, which simplified things quite a bit. All right, well, that's an idea of why L'Hopital's rule should be true, at least in this special case. But let's really look at how you use L'Hopital's rule. So, let's look at the limit. So, example. Let's look at the limit as t goes to infinity of t over e to the t. Actually, maybe before I do that, it would be worthwhile to do one, well, maybe it's kind of concurrently. Maybe we should look at both this and this, just so you'll be careful with L'Hopital's rule and not get carried away on every problem thinking, oh, I'll apply L'Hopital's rule. So, as t goes to infinity, the numerator goes to infinity and the denominator goes to infinity. So we can apply L'Hopital's rule. Now, what L'Hopital's rule says is if the limit, something about the limit of the derivatives, it's if the limit of the quotient of the derivatives exists, then this exists and it equals the limit of the quotient of the derivatives. What we write is kind of what we did when we were working with limits before. We go ahead and write that they're equal, even though if this one doesn't exist, then it doesn't have to equal this one. But we go ahead and write that they're equal, remembering that this is only true if the limits farther to the right exist. So L'Hopital's rule says, assuming that this limit exists, then it should equal the limit that we started with. But the limit as t approaches infinity of, this is, well, the derivative of, you're differentiating with respect to that variable, t, the one that's doing the approaching. So you get 1 in the numerator, and the denominator you get e to the t. But now, this is easy. This is not an indeterminate form, as you don't get 0 over 0 plus or minus infinity over plus or minus infinity. As t goes to infinity, e to the t goes to infinity. So 1 over it, 1 over infinity, 0. This limit is 0, so that exists, so the original limit is 0. This shouldn't be surprising. When t is large, yeah, okay, the numerator is large, but e to the t is so large, it should just overwhelm it, and it does. The limit, as t gets arbitrarily large, this quotient is 0. What about this? If you try L'Hopital's rule, if you get carried away and start trying L'Hopital's rule, you would say this is the limit as t approaches 0 of differentiate the numerator and the denominator. And then as t approaches 0, the denominator goes to 1. So this is 1 over 1. This is 1. Okay, great. Is this right? Absolutely not. As t goes to 0, yes, the numerator goes to 0, but the denominator is not 0. So you don't get 0 over 0 when you put this in. You don't get infinity over infinity. You can't apply L'Hopital's rule to this. And obviously this is wrong, because you can't, this is a continuous function, and you can just plug in 0. You get 0 over 1. This limit is actually 0. It's not 1. Why did we get 1? Because we tried to apply L'Hopital's rule in a situation where you're not allowed to apply L'Hopital's rule. Don't do that. Very bad. All right. But while I'm on the t e to the t part, let's convince ourselves, really, to do what I'm about to do rigorously, you would need mathematical induction, but it's easy to see what really happens. Suppose we want to take the limit as t goes to infinity of e to the t in the denominator, and not just t in the numerator this time, but maybe t cubed, t to the 5th, t to the 7th. How about just t to the n, where n is an integer? So n is an integer greater than or equal to 1. So a natural number. Then we try, so as t goes to infinity, the numerator goes to infinity, the denominator goes to infinity. So we're in a setting to try L'Hopital's rule. L'Hopital's rule would say that limit equals this limit. The limit, you differentiate the numerator, you differentiate the denominator, and you get this. Great. Well, what does this do? Well, it depends. If n minus 1 is greater than or equal to 1, then as t goes to infinity, the numerator goes to infinity, and the denominator goes to infinity, and so you could try L'Hopital's rule again, right? And this is one of the nice things about L'Hopital's rule. You can try to iterate it. And so, well, does this limit exist? Well, maybe it exists if it exists, or if this next limit exists, then that one should be equal to it, where we differentiate again with respect to t. So what happens? Well, you keep differentiating. The denominator remains e to the t. What's the last one? Well, when you get down to t, so if that exponent is 1, then what you've got over here are all the things bigger than 1 up to n. So you've got n times n minus 1 times, and this goes down to 2, and then you'd have a times t to the 1 over e to the t. This is actually in factorial, but that's not really relevant to us. As t goes to infinity, the numerator still goes to infinity, and so does the denominator. So you try L'Hopital's rule one more time. You differentiate the numerator, and you get a 1 times that constant. You differentiate the denominator, and you get e to the t. As t goes to infinity now, the numerator is just a constant. It's a big constant if n is big, but it's irrelevant. This is a constant, and as t goes to infinity, the denominator goes to infinity. A constant divided by infinity, 0. What does this mean? It means, and we say this in math all the time, that the exponential function, e to the t, grows faster than any power of t. And that's when people say that e to the t grows faster than any power of t. This is what they mean. They mean that the limit of the quotient is 0. Okay, let's do another example. Let's do let's look at the limit as x approaches 0. Of x minus the sine of x over x cubed. Okay. All right. We'd like it's supposed to be an example of L'Hopital's rule, but maybe I've made a mistake, or maybe it's a devious trick like this one where you shouldn't use, the one that was here before, where you shouldn't use L'Hopital's rule. So you should check. When x is 0, you get 0 minus sine of 0 is 0. You get 0 over 0. So yes, we're set up to use L'Hopital's rule. And L'Hopital's rule would tell us that this limit should be the same as the limit as x approaches 0 of 1 minus, so the derivative of the numerator, so 1 minus cosine of x, over 3x squared, assuming that this limit exists. Does this limit exist? It's hard to say. You've still got an indeterminate form, because as x approaches 0, cosine of 0 is 1, so the numerator goes to 1 minus 1, that's 0, the denominator is 0. All right, so let's try L'Hopital's rule again. You would get that this should be the same as the limit as x approaches 0, the derivative of the numerator. So the derivative of 1 is 0, the derivative of cosine is minus sine, so minus minus sine, so sine of x over 6x. Okay, the limit as x approaches 0. The numerator goes to 0 still, the denominator is 0. In fact, we looked at sine x over x a long time ago when we did the derivative of the trig functions, or we're looking at derivatives of trig functions. We know that limit's 1. We can go ahead and see that you get that from L'Hopital's rule, so this limit will be 1/6. But let's check. We still get 0 over 0. L'Hopital's rule says that the limit as x approaches 0 of this is the derivative of the numerator, cosine of x, the derivative of the denominator, 6. Finally, we do not get an indeterminate form. As x approaches 0, cosine of x approaches cosine of 0, that's 1, so we get 1/6. So, yeah, and then in the theorem, you actually backtrack. All right, so this limit did exist, so it equaled this one before we took the derivatives. So this limit did exist, so it equaled this one before we took the derivative. So this limit did exist, so it equals this one before we took derivatives. You don't ever write that. You just know when you're doing this kind of long chain of equalities using L'Hopital's rule that in the end, if you get that something doesn't exist, you have to do something else. That the theorem does not imply that this one doesn't exist just because after you take some derivatives, you get something that doesn't exist. All right, let's do one more example. Let me take a particle. A particle is moving along the x-axis. Its position in meters, so we'll say in meters, is given by x equals 1 minus t times the natural log of 1 minus t for t between 0 and 1, where t is measured in seconds. All right, so the question is, as t approaches, so what is the particle doing as time gets closer and closer to 1? So our question is, my question is, what is the limit of the position as t approaches 1 from the left? Right? What I'm asking is, all right, when t is 1, the natural log of 0 is not defined. Right? When t is 1, this is the natural log of 0. The natural log of 0 is undefined. Remember what the graph of natural log looks like, for instance. It looks like this. So here's like y equals, Here's t. This is y equals the natural log. Well, let me not call it x. All right, t. Well, let's use a completely different variable since we have x and t's already. How about z? So this is y equals ln of z. So natural log is undefined when the argument of the natural log function is 0. So this would be undefined when t is 1. And in fact, as z approaches 0 from the right, as z approaches 0 from the right, natural log goes off to minus infinity. If t is less than 1, then 1 minus t is positive, and as t approaches 0, as t approaches 1 from the left, 1 minus t approaches 0 from the right. So this thing is heading to minus infinity. All right. But the question is, what's the position of the particle doing as t approaches 1 second from the left? And it's hard to say because you get another indeterminate form. We want the limit as t approaches 1 from the left of 1 minus t times the natural log of 1 minus t. All right. If you just plug in t equals 1, you get 0 times negative infinity. Right? As t approaches 1 from the left, this goes to negative infinity. This certainly goes to 0. That's one of our indeterminate forms. If we're trying to use L'Hopital's rule, we need to set this up as either a 0 over 0 or infinity plus or minus infinity over plus or minus infinity problem. So let's rewrite what we're trying to find the limit of in kind of a weird way, but it's to set us up to use L'Hopital's rule. We'll leave the natural log of 1 minus t in the numerator and then write 1 over 1 minus t in the denominator. What? Right? Well, when you take this and divide by this, you invert and multiply. So yes, this is the same as what we started with. Why do this though? Well, as t approaches 1 from the left, the numerator now goes to negative infinity. The denominator, so this denominator, the denominator of the big fraction, this denominator goes to 0. So 1 minus t approaches 0, but t is always less than 1, so it approaches 0, but the denominator is always positive. So 1 over it approaches positive infinity. So the numerator is going to negative infinity. The denominator, the whole 1 over 1 minus t, is going to positive infinity. Yes, we are in a situation where we can apply L'Hopital's rule. And for L'Hopital's rule, it'll be slightly nicer, or substantially nicer, to write this as 1 minus t to the minus 1 power. And now you apply L'Hopital's rule. You take the limit as t approaches 1 from the left of the derivative of the numerator. All right, the derivative of natural log of x is 1 over x. Derivative of natural log of something, you get the 1 over the something. But then by the chain rule, you have to multiply times the derivative of the stuff inside. We're differentiating with respect to t. So the derivative of 1 minus t with respect to t, we pick up a times negative 1 divided by the derivative of the denominator. So this is one function and then another function done to that. You use the chain rule, you differentiate raising to the minus 1 power. So you use the power rule, you bring the minus 1 down, you subtract 1 from the exponent so it becomes a minus 2. And then by the chain rule, again, you have to multiply times the derivative of the inside, which gives us another minus 1. All right. These minus 1s cancel. And so you're left with the limit as t approaches 1 from the left of 1 over 1 minus t divided by a negative, and then 1 minus t to the minus 2. Well, that's 1 over 1 minus t squared. Or I'll write it as this. You can pull the minus sign out, and then how do you here's one fraction divided by another. If you invert multiply, you get a 1 minus t squared divided by 1 minus t, so you get the limit as, I'll move over here, but what we get is the limit as t approaches 1 from the left of negative 1 minus t quantity squared over 1 minus t. Well, it's true you could do this with L'Hopital's rule, but it's a silly waste of time. Yeah, the numerator and denominator going to 0, but you can cancel the 1 minus t. Just because you can use L'Hopital's rule doesn't always mean it's a good idea. You cancel a 1 minus t and you get that this is negative this limit, but as t approaches 1, this approaches 0. So this limit is 0. So, yeah, this limit, the one we started with, is 0. So, or what's the same thing? The answer to this, the particle is approaching 0 as t approaches 1. That's the answer to the question. We could do more calculus on this because it's a little, I don't know, it's kind of interesting. It's when t is 0, you're at 1, when t is 0, this is 1, this is the natural log of 1. So at t equals 0, you're also at 0. So at time 0, the position of the particle is 0. As time gets closer and closer to 1, the particle once again gets closer and closer to 0. Did it stay at 0 the whole time? Well, no, this isn't always 0. Did it become positive and then come back, get positive and come back down to 0? Did it hit 0 in between? Did it become negative and then increase back to 0? Just as a quick combining L'Hopital's rule with, or investigating functions using L'Hopital's rule and more normal derivatives. This is no L'Hopital's rule. This was not part of the original question. Let's take the derivative of this and see, as time goes on, at least whether initially whether x increases or decreases, so we see whether it gets negative and then comes back or what. So just for kicks, dx dt. It's the product rule. It's the first thing times the derivative of the second. So 1 minus t times the derivative of natural log. You get the 1 over 1 minus t, but by the chain rule, times the minus 1. The first thing times the derivative of the second, plus the second thing times the derivative of the first. The derivative of this is minus 1, so we'll get a minus 1 times the natural log of t. These 1 minus t's cancel. We just get a minus 1 that we can factor out. There's a minus 1 there and a minus 1 there. We just get minus 1 times 1 plus the natural log of t. Okay. What can we say about this? Well, our t is between 0 and 1. Between 0 and 1, what just happened? That was a big mistake. It should have been a 1 minus t. That 1 minus t did not magically become a t. And we should still have a 1 minus t right here. Okay. When t is between 0 and 1, 1 minus t is between 0 and 1. You can negate this and reverse the inequalities. And then add 1 everywhere. And so what you get is 1 minus t is greater than 0 and less than or equal to 1. So what we're taking natural log of is between 0 and 1. Well, between 0 and 1, natural log is negative. So we get something, okay, so we get something negative here, plus 1 times something negative. In fact, if 1 minus t is less than 1, natural log of 1 minus t is less than or equal to the natural log of 1, because natural log is increasing. Well, the natural log of 1 is is 0. So yeah, this is negative, and you add that to 1, and then you multiply times a negative number. So what does this mean? It means that, well, sometimes this could be where this is negative, where 1 plus 1 minus the natural log of t is negative, you get a positive number for the derivative, and where this is positive, you get a negative number for the derivative. We should look for critical points, look where this is increasing and decreasing if we really want to know what this function does. So, for t, so our t is between 0 and 1, and we are looking at dx dt, which is minus 1 times 1 plus the natural log of 1 minus t. All right? We'll look for the critical points and then check in between where this is positive and where it's negative. Where is this undefined? It is not undefined anywhere in here because we're not allowing t to be 1. But we do have an endpoint of the interval, so one of the critical points, just because we're restricting to that interval, here's t, here's the t-axis, here's t equals 0. And then, well, then this isn't undefined anywhere, but where is it 0? Well, where does this equal 0? We would need 1 plus the natural log of 1 minus t to equal 0, which means we need the natural log of 1 minus t to be negative 1. If we raise e to both sides, we get e to the natural log of 1 minus t equals e to the minus 1. Why do that? Because raising e to powers, applying the exponential function, taking natural log or inverse functions. So we get 1 minus t should be 1 over e. And then if you put the t over there and the 1 over e over here, you would get t equals 1 minus 1 over e. So, if 1 is here, if we put 1 there, then 1 minus 1 over e, e is about, well, it's between 2 and 3, so this is between a half and a third. So, let's just indicate it here. Here's 1 over 1 minus e, 1 over 1 minus 1 over e. And then the question is the derivative positive or negative in here, and is it positive or negative in there? It can't switch. So when t is very close to 0, then this is certainly negative. When t is close to 0, this gets close to the natural log of 1, which is 0, so this gets close to 1. 1 times negative 1, negative. And then as t gets closer to 1 from the left, this goes to negative infinity. And then plus 1, negative infinity, times and minus 1 goes to positive infinity. So the derivative is positive over there. So what is x doing? What is the position doing as a function of time? If here's 1, here's t, here's the x coordinate. You start at 0, you decrease until 1 over 1 minus e, and then you increase and you come closer and closer to this, okay? But really it's undefined when t is 1, but the limit as you approach 1 from the left is that your x coordinate is 0. Do we really know that it's concave up like I've got it drawn? Not without taking the second derivative, we don't, but why not? We'll take the second derivative and then we'll stop with this problem. Is it really concave up? Is the graph really concave up like I've got it drawn? Let's take the second derivative of x with respect to t. you get the minus sign out in the front. Then times the derivative of this. The derivative of 1 is 0. The derivative of natural log, you get the 1 over 1 minus t. But then by the chain rule, another minus 1, minus 1, minus 1, that's plus 1. You get 1 over 1 minus t. But this is positive for t between 0 and 1. It's always positive. In fact, we had that over here. 1 minus t is positive, so 1 over 1 minus t is certainly positive. So yes, the second derivative is positive, and so my graph is reasonably accurate. The position starts here, it decreases until time 1 minus 1 over e, and then it starts increasing, and the graph is always concave up, and as t approaches 1 from the left, the position comes back to being close to x equals 0. All right, that's lHopitals' rule. That's the end of this chapter on applications of derivatives, except the next chapter is differential equations, and there are a lot which use derivatives, and differential equations are very applicable and have lots of applications. So while they're in a different chapter, you could also call those applications of derivatives.